Okay. So, we have so far characterized what we mean by mean and what we mean by variance or standard deviation. For mean, we have already said that it's if we have two random variable, whether they are dependent, independent, correlated, uncorrelated, we do not care, its mean is always addition. Okay. So, separately you can calculate mean and you just add them, you get the overall mean value of that. But suppose I have some x z which is a summation of two random variable, right, x plus y. So, for that we have said that mean of z should be this. So, that is something we have already proven. Now, let us try to see what happens to the variance. Here we will insert or will say something that x and y are independent. Let us try to see what is the implication of that. So, I would like to calculate this sigma z square, which is the variance of z. Z is a new random variable which is constructed by making x plus y, where x and y are two independent random variables. Okay. So, sigma z square is nothing but we have already characterized that z minus z bar whole square bar, we have already said that. So, this is the average of that random variable minus mean square. Okay. So, now replace z by this thing, z by x plus y and z bar by x bar plus y bar, I can do that. So, this is x plus y minus x bar minus y bar whole square, right. I can club this as x minus x bar plus y minus y bar, oh sorry. Right. So, this can be written as x minus x bar whole square plus y minus y bar whole square plus 2 into x minus x bar into y minus y bar. Now, the overall averaging, we know that it is just a multiplication with PDF, joint or marginal, whatever it is, and then integration. So, integration gets distributed with respect to addition. So, therefore, this must be this bar and this overall bar, right. Now, let us see what is this. This is just sigma x square by definition. This is just sigma y square by definition, okay, by definition of variance. Let us talk about these things. Okay. So, first of all, we can say this, let us try to evaluate this, x minus x bar so this will be x y minus x bar y minus x y bar plus x bar y bar, again it will be distributed. Okay. So, this should be x y bar minus, now let us see, x bar is a constant. So, it will be just x bar y by bar, this is also same thing, y bar is a constant. So, this should be x bar y bar plus x bar y bar. For independence, we have already proven that if x y are independent, then x y bar is equal to x bar into y bar. So, this must be 0. Once this is 0, so if we just go back to our previous this one, that sigma z square is sigma x square plus sigma y square, and this is 0. That is a very fundamental result, that if two events are independent, remember, for mean independence was not required, but for standard deviation or variance, the independence is required, and then only the variance of the addition of two random variable will be addition of their variance, right. This only happens when these two random variables are independent. If not, this factor will always be there and this will not be cancelled out. Okay. You have seen that this factor is 2 into x y bar minus x bar y bar. So, as long as they are not 0, this factor will always be there. Okay. So, that is called, means that is how you evaluate whenever two random variables are independent. Okay. Now, from there a new thing comes into picture. What we do is something like this, that particular thing we have got x minus x bar into y minus y bar, we define that as a correlation between two variable x and y. So, we can immediately see if they are independent, the sigma x y will be 0, we call that then x y are uncorrelated. So, independence means that they will be uncorrelated, but not vice versa. Okay. Because actually independence means a little bit stronger condition. It is just not, independence means x y bar will be x bar y bar, that is all right, but if that happens immediately sigma x y will be 0. Okay. Whereas for independence you need something more, that the PDF has to be distributed. The joint PDF P x y x y, that must be distributed, it should be P x x into P y y. This must be happening, which is a stronger condition. If that happens, we know that they becomes uncorrelated, but that does not mean uncorrelation is just this must be equal to 0. It does not mean that x y must be means having a PDF which gets separated out. Okay. So, always do not get confused with the definition of independence and uncorrelatedness. Generally what we should say, independence is a stronger condition. As long as two variables are independent, I know that they are uncorrelated, but the reverse is not always true. Okay. They might be uncorrelated, still it might not be independent. Okay. So, this might happen because independence requires a stronger condition. So, let us try to see what this correlation captures. It is almost, if instead of x I put, sorry, instead of y I put x, it is actually going back to variance definition, because that happens to be x minus x bar whole square bar. Okay. So, basically your correlation takes you towards the variance if x and y are same. Okay. So, let us try to understand what does this means, what is actually correlation. So, let us try to do some means try to list out some random experiment. So, let us say suppose the experiments are like this, I in a day or in a day what is the temperature, that is one random variable for me. Okay. So, that I record, and also I take another random events which is the selling of soft drinks. Okay. So, how much quantity of soft drinks has been sold in a day. Okay. Let us say these are two random events. So, temperature can be anything, different day I see different values I will be getting, same thing will be happening with the soft drink, means sold that number. Now, let us try to plot them. What does that means? We choose multiple number of days, okay, and this is the x axis and y axis. In x axis we will be plotting what is the temperature in a day, and in y axis we will be plotting what is the amount of soft drink that has been sold. So, this is called a scatter diagram, where every day will be put somewhere. Okay. So, what does that means? A particular point corresponds to what was the temperature on that day and how many, means what is the amount of soft drinks that has been sold. So, every point represents a particular day, it is a sample value of that day, okay, and sample value of this joint event. I am actually measuring two random number and try to plot it over there. Okay. Now, plot these things, it is all fine. Now, if these two events which we could see, that as the temperature increases probably more soft drinks or cold drinks will be sold, right. So, these two events are highly correlated, one actually influences the others. So, what will happen in the scatter diagram also, you will see similar things. Whenever this is high, this also must be high, whenever this is low, this must be low. So, it will all be scattered in that region. Okay. Never it will happen that this is higher and this is lower, or this is lower and this is higher. So, it will not be scattered over the entire thing, this will never happen. Okay. So, if I now, so it will all be scattered in this fashion. If you just write or draw y equal to x, it will be around this. Okay. And then if I just take out from each of the samples the x bar, so what will happen? This will get shifted. If I now plot x minus x bar and y minus y bar, so it will be plotted like this, it will be clubbed around this. Once this kind of plot you are observing, then you can say in the scatter diagram that they are highly correlated. Okay. Similar thing might happen when they are just negatively correlated. Okay. So, you could see a plot like this. What will happen whenever a particular part is high, the other part will be low. It's just negatively correlated. That means if this is high, then that should be low. Okay. And if you have something which is completely uncorrelated, the scatter diagram will show you all over the place, something everywhere. It might be high with low, low with high, both are same. So, all kinds of things you will be getting. If they are uncorrelated, if you take out this means bar x minus x bar and y minus y bar, they will be all populated around 0, okay, everywhere. And then immediately if you take these numbers x minus x bar into y minus y bar, they will actually tend to cancel out each other because it is scattered everywhere, right. They will not produce similar things. Here they will always produce positive number, here they will always produce negative number. Okay. So, if you add them all, probably they will produce a huge negative number, here they will produce a huge positive number. That means they are hugely correlated, either positively correlated or negatively correlated. Okay. Whereas this one will give you almost 0. So, that is where the scatter diagram can help you to see that if two events are correlated or uncorrelated. That is pretty obvious or pretty clear which will be happening. So, basically this sigma xy will tend towards 0 if two events are completely uncorrelated. That means this kind of scatter diagram you observe. Okay. And if that is not the case, probably you will see that they diverge, okay, and they will have a huge value. Okay. And for positive correlation, it should be sigma xy should be generally greater than 0, and negative correlation, this must be less than 0. And there is a technique to normalize it. So, what generally people do, this sigma xy is divided by sigma x into sigma y, that is called the rho xy, just to normalize it. What will happen? Whatever the value of sigma xy, this cannot be bigger than this multiplication, right, because that is the biggest that it can get. So, if that is the case, this will be always less than equal to 1 and greater than equal to minus 1. So, at minus 1 it will be highest negatively correlated, fully correlated, and at plus 1 it is positively fully correlated, and at 0 they are completely uncorrelated. Okay. So, this is how it goes. So, rho xy if you plot, at 0 it is uncorrelated, this side the positive correlation increases, this side the negative correlation increases, it ends at minus 1, it ends at plus 1 because you have already normalized it. So, you cannot get a value bigger than 1. Okay. If it is not normalized, it can be even infinity, right. So, that is the concept of correlation, and therefore, I can relate if suppose I have a random variable z which is x plus y, then I can write now, which was earlier done, sigma z square, that is nothing but sigma x square plus sigma y square plus 2 sigma xy. So, that is the correlation. Okay. So, as long as this correlation is 0, this will be just sigma x square plus sigma y square. Otherwise, this correlation term has to be kept in. Okay. So, this is something you will see later on, that if they are not independent and not uncorrelated, then what is the effect of that, what happens in a random variable where you add two random variables. Okay. So, we see most of the time why we are so much bothered, means so far in the previous class as well as this class, we have been evaluating the addition of random variable. Why we are doing that? Let us first try to ask ourselves why this is so much required in a course like analog communication, that we are so much concerned about addition of random variable. So, you know, in signal what happens? We have already talked about a channel being linear, right. So, if there is noise and the signal being transmitted, most of the time what will happen? Noise and signal will be added with each other. Okay. Now, most of the time noise and signal are independent, both independent and uncorrelated. This is the fact. Most of the time that happens. Sometimes there are correlation. There are noise which depends on what kind of signal has been transmitted, like in optical, that is what happens. If you transmit 1, the amount of noise will be higher. If you transmit 0, the amount of noise will be lower. So, if that happens, there is a correlation also. So, but whatever it is, when signal level you are adding, because the channel is already assumed to be linear, so there will be just addition of these two signals. So, your outcome, which is the output, it is just addition of your regular signal plus the noise. If the regular signal for the receiver, it can still be a random thing, right. If the receiver already knows what is coming in a deterministic manner, he does not have to, he does not bother to receive that. Okay. He wants to receive that because he does not know that there is uncertainty over that signal, and that is why he knows that there is some information in that. So, he wants to receive it. So, that is unknown signal, which is also a random thing for him, and the noise which is being added at the channel or at the receiver, wherever it is also unknown to him, it is random. So, these two signals will often be added, and that is why we are so much interested in addition of two random variables. So, we are characterizing, see, you might be thinking that we are just in the background, we are just doing mathematics, but not necessarily. We are choosing that part of mathematics which will be interesting for us while characterizing a communication channel or means signal processing, right. So, that is why we are saying so much things about addition of two random variables, right. Now, we have already talked about when they are independent. So, if noise and signals are independent, then of course, whatever theory we have talked about independence, that will be applicable. If they are not independent, like we have told optical noise, that is not independent of the signal. So, then of course, the correlation has to be taken into account, okay, while characterizing them. So, let us now try to see that suppose x and y, these are two, let us say, independent random variables. What I know is something like this. I know this for x, what is the associated PDF. Now, we are going to PDF. So far, we were just doing things with respect to measurable quantity, that is this variance and mean. Now, let us go towards more concrete things where everything can be characterized. So, the PDF. So, suppose this x and y, for both of them I know the individual PDF. Okay. Let us also say that these two are independent. So, for independence only we are now proving this, whatever theorem will be proving. Okay. Now, let us say my z, which is a new random variable, which is the addition of these two random variables. Knowing these two PDF, is it possible to get the PDF of z? So, that will be our next target. How do we get that? Okay. So, PDF generally comes from CDF. We can always differentiate any CDF to get PDF. So, let us characterize the CDF of z, which is nothing but probability that this random variable z will be less than equal to some defined z over here. Okay. So, from here what do we know? We know that I can say y should be, if this is the relationship I know, that always z is x plus y, then I can always say y must be z minus x. I can characterize this. So, this means actually probability that z has to be less than z means probability that my x, which is a, see, once I characterize x, I can get something on y, right, with respect to this z. So, z less than z means actually x, for any value of x which is less than infinity, I must have a y which is less than equal to z minus x. Then z will be less than this z, right. Always I will be able to ensure this. So, this and these two are equivalent definition, very carefully see this, because what I am saying that I need a probability that my z random variable must be less than equal to small z, but I also know that my small x plus small y is equal to small z. So, now what I am trying to see, because I know the joint means I know individual distribution, right. So, that is something I know. So, let us say this particular event is nothing but that I take any event from x, x can take any value, but I need to ensure that my x plus y must be still less than, x plus y will be that z must be still less than z, that means y must have this condition. Whatever the value of x, it must be less than equal to z minus x, then I know that whatever that associated things I will be getting there, the overall z will be always less than this z if I ensure these two things, because z is always being created by the addition of these two. As long as I ensure this, I will be having this, right. So, if this is the case, I can always write this. So, this is again a joint PDF, from there I can calculate this. So, what do I have to do? For x I have no restriction, I can go from minus infinity to plus infinity, but for y I have a restriction, I can go from minus infinity to this value. So, y should be going from minus infinity to z minus x into p x y, okay, inside let us say u w du dw, right. So, this is the joint distribution of x and y. I still do not know, but probably I do not have to, we will see that, okay. But according to my definition this should be equivalent, right. Now, let us try to do something. So, I can write this from minus infinity to plus infinity, okay. So, this is du, and within that my integration minus infinity to z minus x p x y u w dw. I have not separated this integration, remember it is still this integration inside this integration, I am just writing it in this way, okay. So, you can even write du over here, or you can just write du over here, okay, fine. Now, what I will try to do is I will try to differentiate this, because I want PDF of this, right. I will try to differentiate this with respect to z, that must be giving me the PDF of z. So, p z z, I know that is nothing but d d z of f z z, which is nothing but d d z of integration minus infinity plus infinity, I have du, and inside I have integration minus infinity to z minus x p x y u w d w, right. I have this. Now, this integration limit has no z, so I can take this differentiation inside, no problem in that, only inside of this I will not be able to take, because limit already has z. So, I can write it minus infinity plus infinity d d z. Now, because the limit is z minus x, I will put that as d d z minus x. Of course, I can put a chain rule, so I can write this, no problem in that, and I will have this integration minus infinity to z minus x p x y u w d w, right. This is just one, Okay. What is this? You have this conjugate of integration and differentiation. Okay. So, this differentiation and this integration, they will cancel each other, okay, because that is just complementary. So, they will cancel each other, and what do we finally get? Minus infinity to plus infinity. I will have this p x y or u w, right. Is this fine? Wait a second. So, that should be with that limit. Sorry, I should not write this. I must be writing minus infinity plus infinity. See, whenever I do this cancellation, what will happen? This will just be up to that function, up to this value. This integration and differentiation gets cancelled, but after cancelling, the value that remains is that value, right. So, I can write this as p x y. This u now becomes the x, okay, and w becomes up to this z minus x, and I will be having, if it is x, I will be having x. Okay. So, I did nothing. Instead of x, I have taken a dummy variable dx, okay, and this automatically goes up to z minus x. So, p x y, that goes up to z minus x, this gets cancelled out and it is at that functional value, right. So, that is what I get, and I have, after all these things, I have this thing, right. Now, if these two are independent, I have already told that p x, this x and y are independent. So, immediately I can write minus infinity to plus infinity, this must be p x x into p y z minus x dx, right, as long as they are independent, otherwise no. What do I get? I get a convolution. You can identify this function. This is just convolution of p x and because this variable is z, so it takes you to z. So, basically that is a very important result, that whenever you have addition of two random variable, if I know individual PDF and if I know these two random variable are independent, see in the proof steps all those things were used. If they are independent, I know that that new random variable created through the addition is having a PDF which is just the convolution of the constituent PDF. That is a very strong result as long as they are independent. So, in our case, when signals and noise, those are characterized by some PDF, if I get an additional signal which is addition of these two, as long as I know signal and noise are independent, I can always say it will be just a convolution of these two PDF, right. So, that is something will be with this, with the help of this we will be able to characterize the PDF of the joint signal. That is a very strong tool which will be required later on. So, probably what has happened with all these things, I will probably end my discussion of random variables. So, we have now got enough tool to characterize our signals and characterize our transmitted signal as well as noise when they get added, and all those things we will be able to do that. But now we will go to another step where this random variable will become a function of time, which is a very obvious thing that happens in signal transmission. So, that particular thing is called random process. So, now with the help of this random variables and associated understanding, we will try to build up our own understanding of random process, which will help us actually characterize noise as well as signals. Okay. So, then only we will be able to talk about a communication which is contaminated by noise, how do we characterize that. So, from next class onwards we will start discussing about this random process and its characteristics. Okay, thank you.